Okay, and sadly, this is probably the most important slide, I think. Okay, so I'm talking about the MIRI imager, fondly known as MIRIM. But yes, here, we, in 2014, well, 2015 is the date on the volume, we published papers in the PASP, special volume of the PASP that describes all of the components of MIRI as an instrument, including a description of the imager and its expected performance, its operational use as well. So you're directed to look at that volume for information. Those papers have been posted on George Reeke's website at Arizona, and any updates to those papers, corrections to the sensitivity model and so on, are provided at this website. So again, I strongly recommend people to look on this site as well. We are actively involved at the moment in updating and discussing the tools at Space Telescope which will describe the performance of MIRI in order to correlate them with the instrument team's idea of the performance of the instrument. But that process is ongoing, so as I say, at the moment, I direct people to go here. Hopefully in 6 months or so, this information will be built into the ETC, the APT, and so on. Okay, so the MIRI imager. Designed, built and tested at CEA Saclay in France. I mean, this is very much led by the French team outside Paris, and I think they did a fantastic job of building the MIRI imager. I should say, of course, that there are other components and other members of the consortium across Europe and in the US that contributed to the imager. Detector module comes from the US, from JPL, filters from Sweden, supported by Ireland and the UK, in fact. The mechanism, the key mechanism for driving our filter wheel, we have a single filter wheel with 18 positions in MIRI built in Germany. Okay, but definitely led by Saclay. Okay, so what is MIRI? So we're diffraction limited image quality, Nyquist sampled at wavelengths longward of 7 microns, pixel scale, which is one of my new additions. I thought that might be of interest to people. 110 milliarc seconds per pixel. Okay. We are subject to, as you saw at Macca's talk yesterday, to the huge variation in backgrounds, which really sets the context for MIRI's performance as a function of wavelength. But the aim always with MIRI is to achieve background limited sensitivity, so a sensitivity which is limited by the shot noise on the radiation provided to us by the James Webb Telescope. The instrument is similar. I haven't provided an optical diagram. It's very similar to what you just saw for the FGS, but high throughput, TMA optical system, low distortion, as we'll see later, and stable and well-defined bore sight. So a simple design, but nonetheless beautiful. And this is it undergoing assembly testing at CEA. And this is the test environment at Saclay as well, with, I think, Mylène, isn't it, one of the test team there. A dedicated cryostat was built, and so the imager was tested as a complete entity in its own right with its own optical, with a telescope simulator prior to delivery. This is back in 2010. Okay. So a reminder of the overall MIRI field of view. Here is the spectrometer, small field of view, but depth in the third dimension here for generating spectral cubes. Alvaro will be talking about this tomorrow. But this is there's a single detector dedicated to MIRIM, and so MIRIM includes the imager field, which is this orangey-colored rectangle here, the coronagraphs that Patrice will be talking about later today or tomorrow are up on the right-hand side here, and then Sarah will be talking about our prism spectrometer, which is fed by a slit here or by our slitless subarray. You can use the prism to disperse light for a point target up here for transit spectroscopy, basically. So the basic parameters of the fields and so on are listed on this diagram for you to look at later. Okay. It is worth noting that the LIO mask does not have any kind of filtering in this focal plane mask that is shown here. So this is actually metalwork, is the black area here. The 4-quadrant phase masks are refractive elements, but there's nothing in the field here apart from this dot. So if you take an image with MIRI, you will get good data in the main imaging rectangle, but also in the LEO mask. Okay, so the throughput of those individual imaging filters then. So I've listed the imaging filters here down the side, being coded by wavelength, by central wavelength. But here are the effective pass bands that you will get if you use them. So this is photon conversion efficiency, which is how we talk about our throughput for the instrument. It bundles together or combines both our filter transmission, the reflectivity of our mirrors, and the detected quantum efficiency of our detector. So this is what you'd get if you want to calculate what you should be using if you want to calculate color corrections or integrating up, across an SED. The other factor it includes is a factor of 0.8 to account for contamination at the start of life. Okay. So here's the observatory background. So this is this does not include the update from Paul Lightsey's recent modelling, but otherwise this is identical to the curve that Maka was showing you yesterday, and it breaks down the overall background into just its the main components of zodiacal light, what we get from nature, and the JWST, what we get from nature, but modified by the telescope. Over on the right then are our sensitivities, point source sensitivities for faint sources as a function of filter position. I tabulate these on the next slide, in fact. These are shown as the black dots. It's important to note that the red dots here are showing what the effective sensitivity is for a 1 millijansky point source. Okay? And so the point I'm trying to make here is that at short wavelengths, your sensitivity is limited by the intrinsic shot noise on the target if you're looking at sources as bright as 1 millijansky. So you can imagine, you can think of your point source flux, and you can scale these red dots up and down and see whether you're going to have to care about shot noise from the source itself, never mind the sky background. Okay. Right. All of this should be built into the ETC and will be dealt with by the ETC automatically. Okay. So here are the sensitivity figures themselves. I mean, this is kind of a reiteration of the previous slide, but with in table form. With the point source sensitivities here, I've quoted extended source sensitivities, and then also saturation limits. Okay, I'll talk about where how the saturation limits are defined on the next slide, because that is sort of relevant. This slide appears to have done something hideous. Unfortunately, my eyesight is so bad. But this is telling you how the bright limit is defined for extended targets. Okay. Right. If you look at the notes, the quick guide or whatever, you'll see big differences between the extended source sensitivities and background limits between this table and the one that you've got there, which is the sort of issue that has to be sorted out within the ETC in due course. Okay. As I say, as part of this exercise, we've had those sensitivity estimates have been in place for a few years now. There is recent and ongoing work, both on understanding the detectors within MIRI, but also at observatory level in understanding the stray light background. And so 2 of those effects are being built into the model as we speak, really, or into our picture of performance as we speak. And I've tried to summarize these in the table just to give you a heads up of what the main effects are going to be. So first of all, we are, it looks like, I mean, George Ricci has been getting involved, in fact, with the inventor of the detector technology, Dutch Stapelbrook, who's chap that a few of you will know from many, many years ago, been involved in infrared detector development in the early days, back in the 80s. And so we suspect that there is quantum yield or photoelectric gain within the detectors themselves. And so I'd say this isn't nailed down as being an absolute certainty, but it's at a level at which we expect it to have an impact on our short wavelength performance with MIRI. Okay, so we have a gain, no real evidence for gain dispersion, which would also have a noise impact, but the gain itself means that is an effect we have to take account of. It effectively means that, we get more noise than expected from a single photon because that photon is being turned into more than one electron, detected electron. So that's one effect. The other thing that's happened recently is that it has been flowed through to us that Paul Lightsey, who leads the Observatory straight light modeling, is expecting to have to update his model with an extra component that gives us higher backgrounds between 10 and 15 microns. Okay, so this is higher straight light background, almost certainly coming through the sun shield. So what I've tried to do, I mean, I've been discussing how we implement this with George and come down to these scale factors that I've tabulated here. So these numbers here are the sensitivities that you should see on the previous slide, and then scaling it by these scale factors which account for this quantum yield and this higher background flux. Things are going up slightly, okay? Not by much, but 20%, 15%, something like that. The quantum yield also has an impact on our bright source limit, bringing those numbers down a bit because now we get more signal per photon, so at the short wavelengths. So that has to be taken into account as well. Again, the aim is these numbers will be a target for the ETC. Okay. Right, I did want to say a little bit. I'm going to come around here. My eyesight is becoming shocking, actually, and I can only really see these slides up here. I can't really see the screen. Anyway, I wanted to say a bit more about the saturation limits. Okay, the baseline for observing with MIRI is that you will take 5 frames as a minimum up the ramp. Now, that is for reasons that Dan touched on yesterday, we at the moment, our baseline is to throw away our first frame, throw away the last frame for specific detector effects, and so you want enough frames then to measure a good slope. And so the minimum that we recommend is 5 groups or frames per integration. However, things that most astronomers their favorite targets are generally too bright for MIRI to see under those circumstances. So there's a lot of interest in going to higher flux levels, or be able to detect higher flux levels, and so using less frames up the slope. I interchange the words frames and groups because for MIRI, it's always 1 frame per group. Groups and frames, they kind of mean the same thing for us. Okay, so the quoted saturation limits in the PSP papers are based on this criterion, okay, but they are essentially for 2 full frame reads. That's the baseline that we use, okay. But this is not formally an approved observing mode, as I say, and it's certainly not something that we're going to be intending to provide good calibration optimized pipeline performance with. So there's going to be a bit of a shared risk associated with using these shorter frame times, or shorter frame counts rather per integration, but hopefully we'll be able to use 1 or 2 frames per integration. I mean, the use for this, I mean, people are interested from the exoplanet community, certainly, but I think another interest is for the MRS, for observations of gas giants. So Jupiter, Saturn, they really will saturate if you can't use, certainly at longer wavelengths, 15 or 16 microns, they start to really heavily saturate if you can't use 1 or 2 frames per integration in fast mode. Okay. But of course, we have the preferred mitigation for bright sources is to use subarrays, and I will. I'll move on a bit. But so you've seen, I think Mac had talked about this yesterday. Here again is another image of showing where our subarrays fall. Coronagraphs on the left. These are the dedicated imaging subarrays, as Mac has said. The bright sky, the sub 256. These diagrams even look the same, which is great, isn't it? What I have done, though, out of interest, is superimpose on these on our an image taken with our onboard calibration source. This is a source that we would use for providing interpolated absolute flux calibrations between observations of astronomical flux standards, which may only take place every 2 or 3 weeks. So if there is any sign of drift, then you could nail that down using our onboard sources. It can actually also be used for making pixel flat fields. So 5. I'm better as I go faster. So yeah, okay. Okay, so, and then as a heads up, here are the, okay, so how I've quantified these are gain in bright source limit. This is like the speed gain, so normalized to our full frame. So as you go to the subarrays, these are the gains in bright source limit that you could expect to get. Okay. little bit about image sampling and encircle energy then. So what do the image sampling dimensions look like in practice? So I've got images taken from CV3 testing at Goddard using the fantastic Goddard OSIM source. Here's a 5 micron point source here, okay, which, you know, our PSFs are looking great, as they should do from the design. This is on a log scale though. And so, you know, our aperture is predicted to include about 60% of the flux from a point source in our shortest wavelength filter, and you can see that there's our photometric aperture that we use in our sensitivity modeling at least. Okay, seems about the right thing. There will be an impact on our performance based on telescope alignment. So here, this is what we use. Our black line corresponds to, I think, a 2 millimeter defocus of the OTE of the telescope. Worst case would be 5 millimeters, best case, perfect focus. We'll get a slight performance boost in terms of the sharpness of these images. Another thing that's worth noting though, I mean, our PSF is very well described at long wavelengths by the JWST's diffraction profile, so what's called web PSF, that model. However, at short wavelengths, we have a cruciform pattern that starts to appear, which hopefully you can see in this image here. This is a CV2, this one, test image. You see the point source. If you've got great eyesight, you'll see the JWST diffraction profile to some extent, but superimposed is this cross structure, which we assign or we think is due to scattering along the rows and columns in the detector substrate, in the multiplexer, in fact, behind the detective layer in the detector. Okay, so we developed a model of that. Here's a model plot over on the right here. And so 22% of the point source light in the shortest wavelength is going into this cruciform pattern. And so that will need to be taken account of. Right. Distortion, I think, was on the list of things to talk about. This was measured at Saclay using this incredible grid of points. And so we have actually got a very good, you know, a high quality picture of what the distortion is, at least between the MIRI entrance focal plane and the detector. The distortions in the telescope need also to be factored into this, but they're fairly small and they're certainly very well behaved. But you can see that our projected, I mean, our linear distortion is 1 or 2%, but that translates into a projected area onto the focal plane, which varies by less than 4%. I think that's the peak to peak on this curve, but I can't read the numbers on there now. And there's an image, this is an image of projected area on the sky, okay, as a function of pixel. Okay, nearly at the end, Dither patterns then. So there's, you know, if we look at our operations concept document, that's what OCD stands for, there are a wide range of exotic dither patterns that are going to be made available through the APT for you designing your observations. The key thing for MIRI is that to get our optimum performance, the target must be moved on the detector every few minutes by a distance far enough to move your image, your interesting image, off and get background there instead, okay? And that has to happen every few minutes in order to overcome our issues with stability, to get optimum sensitivity. Of course, that's not going to be the case for transiting photometry or spectroscopy, where you're going to have to sit there and just take it. Okay, right. So that's our primary issue. However, in general, the observations will need to be different. You'll need to subtract off a background level, and that will, of course, add noise if you're differencing two measurements. Potentially route 2 for faint sources, and this should all be budgeted by the ETC. It isn't quite as simple as just a route 2 for faint sources. Well, it's as simple as route 2 for faint sources, but source brightness may come into account. Okay, so that penalty may not be too bad if you have a bright source. Okay. Anyway, range of patterns provided. The unpronounceable one in the mirror and in the middle here, and then Rouleau or something, Rouleau. And then there are these other dither patterns, which in general you'll see do not move the image directly along a row or a column in order to avoid those problems with this cruciform pattern and with the other a long row and the long column issues that you might get with these detectors. Okay, so I was prompted, I think, to talk about strengths and weaknesses, which is pretty well like which of your children do you really care for most, I think. And so I think, yeah, strengths, well, built by a hero. I mean, yes. You know, so no, I think I have a great deal of confidence in the imager as an instrument. You know, throughout I've been involved with the team throughout, and I think it's been built by a very good team. Okay, MIRIM Detect has excellent cosmetics. I think someone's mentioned that already. less than 300 dead hot or noisy pixels in the science field. I mean, you can see them as little clusters here. Even better, right? You know where they are. I mean, there are other issues. We do have, there are little dots on here with Ursh Detre in our team. He has catalogued these like some sort of 18th century biologist, you know. We have, these are bits of dust. They're individual little contaminants that have got onto the detector. They change. Some of them change. Some of them go away. But those are all tracked. They're all down at very low levels in the image, so worth knowing about. But basically, the bottom line is it does everything we asked for. This is what I mean when the original requirements for performance requirements were written for the imager. I'm not aware of any great compromise we've had to make since then. Weaknesses, well, okay, we've got two shorted columns. They sit in this, they're about this position here, which I think just set a nice frame for the imager field, but that's worth knowing about. Okay, so you get very high levels of correlation for those two columns because they are electronically shorted out, and that's it. So, questions?